Well, first of all, I'd like to thank Frank for the introduction and also thank Emma, who organised this event. I have to start off with a bit of a confession. The confession is a bit nervous about this lecture, not because of the talk itself, but because of the audience, about how to pitch it and about the people within the audience. I know there's going to be quite a smattering of A-level students, a few hardcore chemists, undergraduates from here, the odd professor in chemistry, the odd physics teacher, and I mean odd physics teacher, and so I wasn't sure about the level. So I asked Emma, what should I talk about? And she said about 50 minutes. So for the next 49 minutes, I'm going to give you an overview of our work, but really in a very general manner, and I've entitled the talk, What's New with Clean Energy, Batteries Included. For those who've been staring at that, the best way to look at that is, I think, stare for a while and move your head from side to side to get the full 3D effect. If that doesn't work, that obviously makes me smile as well, looking at it from this distance. Also, for those keen observers, some of you have noticed that that crystal structure is not perfect, and more on that a bit later. Okay, so let me give you, since I'm going to give you a flavour of the type of work we're doing, I'll start off with the outline or menu. And really, what I want to do with this talk is divide it up into a couple of short starters, a main course, and then a dessert. The first starter, a bit of introduction on the topic of clean energy, the actual energy demand globally. And the second of the short starters, I'll explain crystal structures and crystal gazing, particularly using quite powerful modelling techniques. And the first main course, I'll talk about fuel cells. Most of you would have heard of the term fuel cell, but I'll try and explain what a solid oxide fuel cell in particular actually is. And lastly, the dessert, I'll talk about lithium batteries, which have helped to revolutionize portable electronics. So love them or just about tolerate them, the mobile phone is with us, and in true theatre or cinema style, I hope you've turned yours off. So let me move on to clean energy. I think it's well established. I think if you pick up a newspaper or listen to the radio news, a day doesn't pass where the topic of energy doesn't come up. And it's because the demand for energy is growing, and it's growing at a very rapid pace because of industrialization in the developing countries. And the problem with that is that most of that energy demand is the use of fossil fuels, oil, gas, and coal. So we have the corresponding increase in CO2 emissions. So likewise, the topic of global warming and potential climate change is a very hot topic, both literally and metaphorically as well. But also with that, there's the human cost as well, because if there's going to be severe climate change, it's going to affect the poorest people in the poorest countries the most first. This talk isn't really about the background on CO2, human-induced CO2. The data really is well documented within the United Nations Intergovernmental Panel on Climate Change, but also there's some really good summary reports in the Royal Society website in the UK. So with that, you've got this very large carbon footprint produced globally, and really we want to look at greener alternatives to fossil fuels. So what will those green alternatives be? I did think on this slide to put a really kind of profound quote from a US president or a Nobel Prize winner, but I went for another profound philosopher, and that's Kermit the Frog, and it ain't easy being green. So what are the green alternatives? I think what's clear is that over the next 20, 30 years, there's going to be a move towards much more diverse energy mix. It's already happening, and that mix will include solar cells, photovoltaics, it'll include wind, it'll include next generation biofuels, tidal and wave, And obviously we can do our bit by energy conservation, either energy-saving light bulbs, energy-efficient buildings, maybe using or moving away from dirty 4x4s. But what's obviously less clear is the economic and political factors are uncertain. But as scientists and engineers, we can make a contribution in trying to further these technologies. And the two technologies that I'm involved with are very much chemistry-based, what I call electrochemical technologies. The first one is fuel cells, which I mentioned in the introduction. And they've been trialled out in very successful London buses, as well as other buses around the European capitals. They're polymer-based. The ones I'm going to talk about are probably the less sexy end of fuel cells, and that's to do with solid oxide fuel cells for homes and buildings. And I'll explain what a solid oxide fuel cell in a moment. The other technology, which is electrochemistry-based, are lithium batteries. As I said, they've revolutionized portable electronics, but can they make a contribution to hybrid or electric vehicles, which are coming on the market at the moment? So this is the less happy face oil and the happier face battery. And both, as I've noted here, both rely on crystalline materials. So they rely on chemistry for their function. So for both of them, if we want to have some advances, there's a big materials chemistry challenge. And this is really a challenge that materials chemistry have taken up with gusto. And the challenge is really, we need to develop new materials, and we need to understand them to a greater extent. So really, this sums up my research philosophy, the need for new materials and a greater understanding. So that's the challenge, and hopefully I'll explain some of the advances in the next half an hour or so. So what are the key questions I'm going to address during this talk? Well, the first one are, how are solids imperfect? Some of you may be aware of crystalline materials, but they're not perfect. So how are they imperfect? What is a solid oxide fuel cell? And how do lithium ions move within the phones that you've got probably with you? And the last mystery is, was William Shakespeare a materials chemist? So hopefully I'll be able to answer that controversy. As I can't answer the other Shakespearean controversies, but hopefully that one. So let me move on to the second of the starters, and that's to do with crystal gazing. Not the New Age variety, but more to do with chemistry. So I hope most of you are aware that common garden salt is a very regular crystalline material. So the things you sprinkle on your chips or pasta has a regular structure. And the regular structure is made up of a very repeating unit, a regular repeating pattern, which extends in 3 dimensions. So that bonding within sodium chloride extends in 3D. And that 3D is represented by this sort of little motif, and that's repeated continuously. So that's just the 2D representation of the rock salt structure. And a good analogy is wallpaper. I couldn't find any wallpaper. Most people don't seem to use wallpaper anymore. So I went for the old motif. It's familiar to Harry Potter fans. But what happens with this regular repeating unit is that you can form sort of a wallpaper design. And that's repeated in 2 dimensions. So if you wanted to see a 3D, then you can get a 3D image, which I'm going to show in a second. So before that, let me answer the first question. How are solids imperfect? Well, this is a beautiful painting by Salvador Dali, and it shows an image of a human. What I like about it, it's almost showing a crystalline lattice. So it blends the human with a crystalline lattice. And this is a quote from a good friend and colleague, Sean Corish, in Dublin. And he said, like people, solids are imperfect, making them unique and interesting. The next quote is from me. Like solids, some people have more defects than others. I know I've got quite a lot. My bad jokes for a start. some would say perhaps city bankers or News of the World editors, but I couldn't possibly comment. But what's interesting is that these solids are imperfect by nature. They are imperfect because they introduce disorder. Just like a teenager's bedroom, it tends towards disorder. And that disorder is intrinsic to these crystalline materials. So let's go back to our 3D glasses. So red, as in politics, red on the left. And so if you stare and move your head about, you can get a good idea. So that is the sodium chloride, rock salt, that you sprinkle on your food. And as I said before, the bonding, ionic bonding, happens in all directions. So it's three-dimensional. The sodium ion is the small ion. The chloride ion is the large ion. So that's the rock salt structure. So let's move on. So the silver chloride has the same structure. It's the rock salt structure. But in this case, this is the title slide. And I hope you can see that this crystal structure is not perfect. There are some defects in there. And I don't know if this will work, but I've got a pointer. Usually it's like the BBC weatherman. I'm not sure what I'm pointing at. But so the silver sort of over here, there is, I don't know what I'm pointing at, the silver ion vacancy, that where that crosses, that silver ion is missing. And that silver ion has moved from its normal site to this site here, which is at the center of that cube. And that's called an interstitial, silver ion interstitial. So that occurs by nature. Silver chloride is imperfect with that kind of disorder. And that's not easy to study by experiment alone. So why do I bring that up? Well, the reason I bring this up is often these types of defect control the important properties of these materials. And in fact, in this case, it was very important to thin film photography. For all of you, for the youngsters in the audience, this is called photographic film. Obviously, the dirty word that Kodak hate nowadays is the word digital. So digital has led to, I think, Kodak, actually the demise of Kodak and Fuji. But that thin film photography, which dominated photography up till digital, was dominated by silver halides, by silver chloride, and those silver defects. So the first ever silver negative image was based on those silver interstitials. They just clustered. So that's a good example of where defects are important. And the other area where defects are important is that these defects are not stationary. They don't stay where they are. And these defects control what is called ion conduction. So that's the silver chloride, and you can, the next bit, you'll see the ions moving out from the lattice. Who needs Avatar? Okay, so that's, let me show that again, because I quite like it. So that's the silver ions moving through the lattice. The text that comes up indicates that the pathway, that's a very simple mechanism, silver ion going through the rock salt structure. But most materials aren't as simple as rock salt. And most materials, you don't know how the ions are moving. And this is, hopefully I'll show you that with sophisticated techniques, you can begin to understand how ions move within the crystal lattice. Okay, so, right, so specs off. So let me introduce one final type of defect, and that's to do with what I've called dirty crystals. These are beautiful gemstones or emeralds, so nothing on the smutty side. So these are dirty crystals, and those impurities really control the beautiful colors you see in these gemstones. Without those impurities, you wouldn't get those range of colors. And this allows me to introduce the fact that not many people know this, but Shakespeare, as well as being a brilliant writer, was probably also a solid-state chemist. In Midsummer Night's Dream, when Demetrius wakes up and sees Helen for the first time, he says the following words: "To what shall I compare thine eyne? Crystal is muddy." And what Shakespeare is saying here is, compared to Helen's beautiful eyes, crystals contain ionic impurities. So I'm sure if you look at Shakespeare notes, those notes, that's explained in there. So Shakespeare, there is some controversy, but I think he was a fantastic solid-state chemist. So let me move on to the last of the bits of the starter, and that's to do with computer modeling. So when I go to dinner parties, or any party if I'm invited, if they ask me what I do, rather than say I'm a chemist, I sometimes say I model. But it's not to do with, obviously, modeling down the catwalk, but it's computer modeling down the, I suppose, the computational catwalk. And this is a line from an RSC poster, "Not all chemists wear white lab coats," and it really sums up what I do. And so what is modeling? Well, modeling basically allows you to use existing knowledge about a crystal. The existing knowledge is that bonding in solids, or nature's glue, can be represented by well-known forces. Those forces are well established. They're ionic bonding in all directions. There's attractive and repulsive forces. And what these mathematical models those forces can be represented by mathematical models. But what the computer is very good at doing is doing the number crunching. It can basically number crunch to work out the forces within that very large crystal. Remember, these aren't molecules. These are extended solids. So what can you do? So a good analogy is this beautiful or iconic photo of James Watson and Francis Crick. So back in 1953, they managed to build up this structural model of the molecule of life, the DNA. And they just used clamps and retort stands. And they subsequently got the Nobel Prize for that, I suppose, discovery of the double helix structure for DNA. Nowadays, you can do that within seconds or minutes on your powerful computer. You can get out that computer model. So what are the aims of modeling? Really, the aim is, can you get further atomic scale insight and into that crystal structure, and can you be predictive? Can you predict something about those complex solids on the atomic scale? So the things we're looking at are the crystal structure, we're looking at how ions move, the defects I mentioned, a vacancy, the Shakespearean type dopants, and lastly, the surfaces. And you'd have heard about, obviously, the nanoscale and catalysis. That relies on surfaces. Can you understand a bit more about surfaces? So that fundamental knowledge or science underpins the technology. So that ends the starters. Let me move on to the first main course. That's to do with fuel cells. So a bit of history first, and the history relates to one of my scientific heroes, and that's Michael Faraday. And he was on the back of the old £20 note, and this is him giving a lecture, infamous lecture within the Royal Institution in London. I've dubbed him the godfather of ion conductors, and that's because he really started off this field of electrochemistry by discovering that solids, certain solids. So in his diary, or I suppose the tweet of his day, I'm not sure if it's less than 140 characters, but anyway, the tweet of his day in 1835, he said that materials, when sought for, would conduct electricity in the solid state. So he observed ion conduction in the solid state, and that led to this whole field, one of the main fields of electrochemistry. So why is that important? Well, it's important for both fuel cell types. Both rely on ions moving within the cell, within the electrochemical cell. So, as I said, the sexy end is the polymer side, which are used for cars, although the big challenge here is to do with hydrogen storage and hydrogen production. The area that I'm working on is really a stepping stone technology. It doesn't have to rely on hydrogen. It can use other hydrogen-rich fuels. And this is the solid oxide fuel cell. But there is a problem with the solid oxide fuel cell, and that's to do with temperature. It relies on very high temperatures, and it is quite costly, so you need some lower temperature materials. So this is one of our areas of research, to look at new materials for these solid oxide fuel cells. So I should explain what a fuel cell is. Well, it's based on the topic electrochemistry, and it's a very wide topic, but in essence, the topic is about generating electrical energy from a chemical reaction. Okay, obviously there's much more to it than that, but in essence, that's what you're doing. And it also applies to batteries as well. So let me show you a schematic. I've dubbed a fuel cell electrochemical sandwich, because just like any old sandwich, it's got some bread slices, which are in grey, which are the electrodes. And like a sandwich, you've got the meat, or cheese if you're vegetarian, between the two bread slices, the electrodes, and that is the crucial bit. So for a good sandwich or a good fuel cell, you need a good sandwich filling. In this case, you need a very good ion conductor. In this case, a solid oxide ion conductor. In the polymer case, that is polymeric. So you have a polymer between those electrodes. So how does it work? Well, it works quite simply by air or oxygen on the, in this case, the cathode side, the electrode side. You've got fast ion conduction across that meat filling or cheese filling, and then it reacts with the fuel, in this case hydrogen, and you've got water. So you can't get any cleaner than that. The reason why it's a stepping stone is that the fuel on the left-hand side in a solid oxide fuel cell could be methane or methanol. So it could be hydrogen rich. So it can actually fit in to current infrastructure. In fact, British Gas are trialling out some of these solid oxide fuel cells within homes using methane. So that is, and as you can see, it's very efficient, it's very clean, and it's fuel flexible, as I've said there. And currently, air is still free, although I'm not sure with this current government. But that's, it's a very, hopefully, a clean process. Because of time, I'll miss on that. So this, back with your 3D specs, I mentioned that the problem with the current fuel cell is that they rely on high temperature. This is the current ion conductor. This is the current sandwich filling in between those electrodes. It's an oxide. It's zirconium oxide, typically doped with yttrium, but that's not critical here. What I wanted to show you is that the structure is very different, not very, but it is different from the rock salt structure you've seen. It's still cubic, but I hope you can see it's a much more open structure. And that's because for every zirconium, there are two oxygens. So the ratio of cation to anion is different. And you've got, right in the middle there, there's quite a lot of space. So this particular structure allows ion conduction after it's been doped. And that structure is called the fluorite structure. So it's a very good ion conductor, but at very high temperatures. So as I said, I'm moving on to some new materials, and it allows me to use a very bad pun, an appetite for fuel cells, and I have to warn you, there's worse to come. So what are appetites? Well, the ones I'm looking at are new, but there are well-established biomaterials. And the biomaterials are based on calcium hydroxyapatite. So they actually occur in our bones and in our teeth already. So there's a nice big schematic just to emphasize that. Why the interest in apatites? Well, there are some new synthetic apatite silicates based on, the ones up here are based on phosphates, the new ones are based on silicates. And surprisingly, or maybe not surprising, but they do show very good ion conduction. Although think about it, I'm not sure if anybody's tested out ion conducting teeth. So I don't know where they've got that. But anyway, these silicates are very good ion conductors. And they are much more complex structures. So what do their structures look like? Well, they're based on silicate groups, and most silicates have tetrahedral groups. And that means that silicon is tetrahedrally coordinated to oxygen. For those keen followers of solid-state chemistry will know the oxygens are often in red, so that's there, silicon's there. But you can represent that tetrahedral motif by this kind of pyramid polyhedra. And I show that because it illustrates, it's illustrated in the next diagram. Silicates are all around us. I mean, in fact, we live in a very crystalline world. If you look at the Earth's crust, it's actually made up largely of quite a lot of silicates in there. And one of the most common is just sand and quartz. So if you get your specs back on, there's 2 or 3 3D images coming up. So this is the beautiful structure of sand, silica, SiO2, silicon dioxide. And as you can see, it's got that tetrahedral motif, that kind of pyramid type structure, and they're all corner sharing. That means that they're connected at their corners. And by being connected at their corners, they form this very kind of network of tetrahedra. You can almost visualize, if you move your head side to side, you can almost visualize some pores, some gaps or channels down that structure. So I show that to show a contrast with the next one. The next one is apatite. And maybe I should stand back a bit here. I hope you can see that one is very different. The tetrahedra here are not connected at their corners. Those yellow tetrahedra are now just, in a way, forming isolated structures. Obviously, they are connected in some manner. The grey ions are lanthanum, and the central blue is oxygen. And as I said, you can see that it's very different from the silica structure. In fact, if you shake your head around, you can see that it's almost like a channel coming towards you. Hopefully, the idea is perhaps to mesmerize you as well. So why is this important? Well, it's important because this particular one showed very good ion conduction. But because it's a complex structure, when it was first discovered, they weren't sure about its conduction pathway or the important defects in them. Keep your specs on. This is a biomaterial related to, the next one is also bio-inspired, but nothing to do with fuel cells. That's a nice, I like seeing this on the big screen. Doesn't look so great on a laptop, but this is Millipede, and what's fantastic about it is those, if you shake your head around, those antennae follow you around if you move your head. So it's quite creepy. So in fact, if I walk around, it just won't leave me alone. So, and if I stand, I don't know if it's wrapping around me, but anyway, that's on a website called 3dimages.co.uk, which I have to acknowledge. Right, so sorry to get you all dizzy. So as I said, why the interest in these silicates? Well, they're a new family of oxide ion conductors at lower temperatures. So the questions are, what is the ionic defect, and how do they move? They're new structures, so they're not well established. So we decided to do some modeling work with neutron diffraction. Neutron diffraction is a very powerful diffraction technique which allows you to look at isolated defects. And we made a discovery that was unexpected. The unexpected result was that the defect was oxygen, which wasn't unexpected, but the location was. This is the structure again. These are the yellow tetrahedra. The blues this time are lanthanum, and the reds are oxygen. So it's a side view of what you saw from the front. This is a side view. And what we find is that this interstitial oxygen isn't in the middle of the channel, as what we thought it would be in the middle, right in the middle of the channel. It's actually in the side, near the tetrahedra. And the next surprise was that we predicted that the path would not be linear, but very curved sinusoidal path down the channel, where the tetrahedra allow that. So curved path near the tetrahedra. What was nice is that neutron diffraction confirmed the position of that defect. So our modeling was confirmed by experiment. What experiment hasn't been able to do ambiguously is this curved path. But we feel confident that we've got the energetics and everything quite right. We're extending that work to look at doping. It's very tolerant to doping. So we've tried to dope it with boron oxynitride, just for the simple reason, for the worst pun of all, to get a bon appetit. I warned you there was some bad ones coming up. That's not the end of it. So we're continuing our studies on this, and in seriousness, we are doping with other things as well to try and improve the properties, because they are very tolerant to a range of impurity ions. Oh yes, so let me show you. It's not quite a 3D animation, so it doesn't match Avatar, but hopefully I can show you if this opens fast enough. So this is a bit of an animation. It's a bit of an exaggerated animation of the lithium ions going, the oxygen ions going through the apatite structure. So the clear tetrahedra are the silicon tetrahedra, and the reds are the oxygens moving, and the kind of blueberry atoms are the lanthanums. So this just shows up a second time. So what I wanted to show to you is that even a crystal lattice is not static. You do find ions moving through a crystal lattice. Okay, so that's the apatite migration. So let me go back to there. So let me end with the dessert, and that's to do with lithium batteries. So I've talked about fuel cells, I've talked about their structures. This is something that you all use. I can safely predict, I'd be very surprised if none of you have ever used any of these portable devices. And the reason why they're portable devices now, including the iPad and iPod and etc., is that the lithium battery has a high energy density. So they're small and light. And it's a very big industry. They estimate about 3 billion cells a year are sold. But it's a fantastic example of fundamental research, curiosity-driven research in the early 1980s in Oxford, led by a guy called John Goodenough, who's now in Texas. He proposed the idea of oxide electrodes, and that led to Sony commercializing the lithium battery cell in '91, which has obviously generated lots of revenue for Sony, etc. So otherwise we'd be stuck back in the 80s like that. So city bankers were city bankers back then. So what's the next challenge? Well, portable devices will stay. In fact, portable devices are developing all the time. So that will still be a big application. But a challenge in terms of clean energy is to do with transport. Road transport accounts for about 30% of CO2 emissions in the Western world. Okay? The problem with that figure is, unlike other areas, that figure seems to be predicted to grow, because car ownership, particularly in the developing countries, in India, China, etc., is growing. So can we develop hybrid or electric vehicles? And these are a couple of examples. The Toyota Prius, which is a hybrid electric vehicle, which uses not lithium battery, but nickel metal hydride, which has its downside because it's not as energy dense as a lithium battery. But over 3 million of those cars have been sold. I suppose the other end, the more expensive end of electric cars, is this Tesla vehicle here, over I think £100,000 if you've got spare cash. But what's interesting, as I was doing some research on this talk and other talks, that 80% of daily car journeys in Europe are less than 40 miles. If you think about it, it's to do with the school run, it's going to pick up shopping from the supermarket, and even the daily commute, often daily commutes, are less than 40 miles. So the long journey, there's this phrase called range anxiety. They're worried about electric vehicles not going far enough. Well, actually, for urban driving around Manchester, London, whatever, electric vehicle would be sufficient because you're actually not going very far at all. So electric cars are definitely getting the green light. I think you're going to see more of these charging points around. This is a plug-in electric. The Nissan Leaf is being manufactured in Sunderland, so that's happening this year, and that's a pure electric vehicle based on a lithium battery. And this is a schematic of such an electric vehicle. This is a hybrid where there's a fuel tank and electric motor. I show this because I'm not a car engineer, but I like this because it's got this fantastic label at the top here. Battery recharge plug, not to scale. I do like that, you know, as if you're going to buy a car with this massive plug behind it, you know. But I do like that, not to scale. So what are the lithium battery materials? So lithium battery cell taking charge. So I hope I'm going to give you an idea of what your phone or iPod is doing when you plug it in tonight or whatever. And what's happening is you're charging your lithium battery. And that lithium battery is made up of, just like the fuel cell sandwich, you've got this couple of bread slices, the oxide electrode based on lithium cobalt oxide, very sheet-like structure, very layered structure. Graphite, as you know, is very sheet-like as well, very layered structure as well. And what happens on charging, the lithium ions go from the cobalt oxide electrode, it basically is pushed uphill to the graphite electrode. So the lithium ions are going that way. And that's what your little green symbol is indicating. But when you're using your phone or device, the opposite happens. You get discharge, and the lithium ions are going the other way, but electrons are powering your device. So basically, it's a beautiful example of electrochemistry and a beautiful example of materials chemistry, because that cobalt oxide was developed by materials chemists back in the 80s. So what's the problem? Well, the problem is cobalt. It's expensive, it's toxic, and this cell is probably not safe enough for electric cars. It probably is safe enough, but safety legislation is much more stringent these days. I mean, if someone told you I've invented this kind of tin can which runs on this very flammable liquid called petrol, it wouldn't get past the safety, but now we just go around in it quite naturally. But we're looking at alternatives, and before I look at the alternatives, I want to explain what the cobalt oxide structure looks like first. So this is a little segment of the cobalt oxide structure. It's connected to 6 oxygens in this octahedral environment, which we can represent, just like the pyramid before, an octahedron here. And what this leads to is my final 3D images. And so those octahedra are basically sharing edges. By sharing edges, they form these layers. And these layers form very weak interactions between the layers, allowing lithium ions to come in and out between those sheets. So you can almost imagine, as you're charging and discharging your phone or device, lithium ions coming out between those sheets. So really, those lithium ions are in and out between those sheets. So as in life, the important stuff is happening between the sheets. So, sorry, I had to get that one in. So what are the alternatives? Well, the alternatives have to be sustainable. And the best sustainable material is iron. So basically, you could make batteries out of rust, if in principle. So they're looking at iron-based or manganese-based, particularly iron-based materials. So if you keep your specs on, you'll see the most topical lithium battery material. This is lithium ion phosphate, LiFePO4. And even if you don't know any chemistry, you can see straight away this structure is very different from the layered sheet-like structure of the cobalt oxide. Okay, so let me explain this beautiful structure. It's made up of these yellow lithium ions coming towards you in those channels. The grey octahedra ion oxygen octahedra, and these kind of pyramid tetrahedra are the phosphate groups. So they're sharing corners. But what they build up is this beautiful 3D network structure allowing lithium ions to come in and out of those channels. And it fulfills the X factor. It's got a high voltage, it's non-toxic, it's a lot cheaper, and it's safer. And it's safer because of chemistry. Those phosphorus-oxygen bonds are stronger, and that imparts greater stability on this material. So this material has already been commercialized in power tools for Black & Decker and others. It's already been trialed out in some cars and buses in the US. And there's talk of various car manufacturers in Europe using these phosphate materials. So this is a very hot topical material, and we're studying this. So keep your specs on. This is a 3D image as well. Our research, even though my research is materials and chemistry, we do link up with engineers. And we link up with engineers up in Glasgow. You may not believe it, but this is our test car. This is our test vehicle. This is a hybrid test car. This AC Cobra up in Glasgow. And that's being tested out with lithium battery materials and supercapacitors. As you can see from what they're wearing, it was a relatively warm day in Glasgow that day. So the last one is this is the last 3D slide. Not many people know this, just like Shakespeare, but the old Doctor Who, and probably the current one, that sonic screwdriver is believed to be lithium battery powered. Yes, he plugs it in every night in his TARDIS, and the Daleks are catching up with their hybrid electric Daleks as well. Right, let me finish off about lithium ion phosphate. So lithium ion phosphate is very topical, and I want to talk about two issues. One is to do with the shape of lithium ion phosphate, the shape of these molecules, these compounds, and also how do those lithium ions move. The channel structure suggests 1D, and you'll be right, but there's more to it than that. So crystal shapes, or crystal shapes, another word for crystal shape is morphology, and this is actually a crystal at home. I don't know if anybody would have a stab at guess of what that electron micrograph, that is a magnification of a common crystals at home. Actually, that's the fur within the kettle. So it's magnified by microscopy. So you can see, magnified, it actually looks quite attractive. But crystals have different shapes, and this is the microscopic scale rather than the atomic scale. So small but perfectly formed, that's what lithium ion phosphate is. And this is from modeling, we find this kind of, instead of needle-like shapes, we've got this very plate-like shape. And that produces this thin plate-like shape from modeling. And what was nice is, from a collaboration with a guy called Tom Richardson in Berkeley in the USA, he synthesized these very plate-like crystals. So we helped him actually identify the different surfaces within his crystals. But why is that important? Well, the reason why it's important is that big face on that plate-like crystal is perpendicular to the lithium ion channels. So the lithium ions are actually coming in and out of that big face, which is very important because you want as much lithium ions to come in and out as possible, as fast as possible. The big issue in terms of charging and discharging is how fast you can do it. Obviously, all of us ideally would like to just plug in our phone and get it charged up within a minute. There are problems with that, and that's related to this idea of lithium ions coming in and out. So more lithium ions can come in and out with this large face, and it's important for battery performance. But how do the lithium ions move? So this is a slice through the structure. This shows the blue is the phosphate tetrahedra, the yellow are the iron octahedra, and the greys are the lithium ions. And what we find from modeling is that it's not a linear path. Again, the path of least resistance is not straight, it's curved. So we find this prediction that it's a 1D path, but it's curved. So we predicted this back in 2005. We thought, again, scratching our head, and basically it's to do with energy. It's like all of us, we want to go along the path of least resistance. It happens to be the lowest energy path. And is there some experimental evidence for that? And there is. This is experiments carried out in Tokyo by Yamada and Shima. And these experiments based on very sophisticated neutron diffraction again. And they found, indeed, that the lithium ions are going in that 1D channel, but not in a linear path. It's actually going along this curved path. So it confirms our prediction from modeling this curved path. So that was one of the aims of modeling. Can we be predictive? So that was quite nice. And we've extended this work to a whole range of other materials as well. So let me begin to conclude. That was the dessert. Let me just say some take-home messages. I hope I've shown you, despite some of my bad puns, that materials chemistry is crucial to some of these clean energy applications. And I hope I've shown you also that a lot of these materials are very intricate and beautiful on the atomic scale. In fact, I would argue just as beautiful and aesthetic as the arts. I hope I've shown you some insights. If there's two words you're going to take away, is the word defect in a solid, and also that they conduct ions. And both of those are important in a lot of these solid state applications. And the last one, I hope I've started possibly an important controversy that Shakespeare is possibly a materials chemist. So what does the future hold? I think the future, well, I think one thing is certain about the future, and that's that it's uncertain. With the current economic turmoil, as well as the price of petrol fluctuating all over the place, it's very hard to predict what's going to happen. But I think, well, I hope that these two technologies will begin to develop or be used, both relying on chemistry. The fuel cells being trialled out by British Gas and Ceres Power, lithium batteries within electric vehicles. And I think for science and chemistry in particular, I think it's a challenging but very exciting time to be a scientist in the 21st century, because we're involved with a whole range of important things like sustainable materials, clean energy, nanoscience, and fields outside this area in terms of health, medicine, and water all rely on chemistry. Last year, I know we've slipped into 2012, but last year was the year of chemistry, the UNESCO Year of Chemistry. So I thought I'd show this slide again, and it was celebrating the 100th anniversary of a remarkable woman, and that's Marie Curie. It was a 100th anniversary of when she won the Nobel Prize for chemistry in 1911. She's remarkable for a number of reasons. One, she's actually one of the rare people to win the Nobel Prize twice. She was a very successful woman in a very male-dominated world, if you think of the beginning of that century. And she won the Nobel Prize in 1903 with her husband, Pierre Curie, and Becquerel for physics. And I hope that some of you will have an impact in the future as well, as future chemists. I hope I've shown you that chemistry is very important, so hopefully some of you will be involved. So let me end with some thanks. So really, I'm the kind of the front end of the research. I have to thank a fantastic research group and collaborators. There's Pooja, David, Jesse, Graham, Chris, John, Alison. Alison, she helped me with the 3D specs. Emma, Craig, and the two collaborators, the two Peters, Bruce and Slater. They all seem very happy. I think it must have been when I mentioned I was away for 2 weeks or something. Anyway, also for inspiration, a couple of photos, a couple of young ones back at home who give me joyful inspiration, Yasmin and Zach, and very cute. And also thanks to the RSC for supporting this lecture, the EPSRC for funding my research. I didn't get a chance to kind of cut and paste, but also thank Manchester, the STEM group, Emma, Frank and others, for really organising the event today. If you want some further information, you can Google Saiful Bath. I promise you won't get a dodgy image. I think I end up being the #1 hit. And these 3D specs are being funded, so you're welcome to keep them. I've actually set up the 3D images as a PDF file on my website. So if you do Saiful Bath, if you click on lectures, I've set up a PDF. So if you want to show friends and family those 3D, you can keep it. But if you don't want to keep them, I do recycle them, so you can leave them behind at the top. And finally, thank you for coming, but I've got one final quote, an end quote. And being a devout Darwinist and humanist, I went to this fantastic exhibition on Darwin at the Natural History Museum. And there was a great quote, not from the great man himself, one of the greatest scientists that ever lived, but the quote was from a French philosopher and writer, Marcel Proust. And to me, it sums up science in general, but materials chemistry in particular. And the quote is, "The real voyage of discovery consists not only in seeking new landscapes, but in having new eyes." And on that note, I'd like to thank you again.